This video introduces TrueShape Descriptors, the local descriptors used by the Echelon algorithm. The demonstrations presented in this video are based on frames from a clip of a rotating head, shown here. The demonstration begins with a brief tour of the Echelon test bench, a software application developed to verify the theory upon which the Echelon algorithm is based. Here, I'm loading 2 consecutive frames from the rotating head video shown earlier. The images I'm retrieving will fill the 2 frame buffers used by the Echelon algorithm to support side-by-side frame processing. Once the frame buffers are loaded, processing is applied to each frame using the Setup GUI. The Setup GUI allows a separate scale space tree to be extracted from each frame of video, like this. Once a scale space tree has been extracted, the software displays the highest tier in the corresponding scale space image, in this case, tier 54, as indicated here. As with all images, the corresponding tree has a single trunk, represented here by the local extremum inside the yellow circle. Next, I'll trace this local extremum back to the first tier in the scale space image. In doing so, the software has traced one of the many stationary curves, or branches, that make up a scale space tree. To explain TrueShape descriptors, this demonstration will look at a single descriptor site for the region corresponding to this interface point near the eye. An interface point is simply a local extremum in the first tier of a scale space image. Interface points are the tips of the branches in a scale space tree. Tracing this branch will then lead to the branch's top point, as follows. The branch's top point is the last point in the branch just before the yellow circle disappears. Activating the top point overlay will show that the algorithm has in fact detected the point inside the yellow circle as a top point, as indicated by the green dot. Every top extremum has one corresponding top saddle point. The top saddle point in this case is indicated by this blue dot, adjacent to the green dot. Turning on the ISO contour line overlay helps clarify the relationship between a top extremum and its top saddle point. As an aside, the name saddle point arises because the topology around a saddle point is shaped like a horse's saddle. To continue the discussion, a screen grabber is used to transfer a copy of this scale space tier into Microsoft Visio. The set of local extrema used to derive TrueShape descriptors are joined to each other by a series of paths that originate at the same top saddle point. Here, I'm adding a larger dot to make it easier to see the top saddle point used in this example. Next, I'll sketch the paths that join the set of local extrema needed to define the TrueShape descriptors derived in this example. The paths I'm sketching are referred to in the literature as relative critical paths. While tracing each path, I'm attempting to follow a course that remains perpendicular to each ISO contour line that the path crosses. Now, I'm adding a dot on top of the raw data recorded by the Echelon algorithm so that the data can be cut and pasted to another sheet. Here, I'm lifting out the points needed to describe how a TrueShape descriptor is derived and pasting the points into a new sheet. In the three-dimensional scale domain, the points and curves shown here lie in the same plane and establish a figurative garden, complete with walking paths. The data is referred to as a garden set. Here, I'm extracting the 4 local extrema that make up this garden set. TrueShape descriptors quantify the relative position of the local extrema in a garden set. This relative position information is embodied in 6 line segments that connect the 4 points to each other, as I'm demonstrating. Next, I'll add arrowheads to 2 of the line segments originating at the same local extremum and ending at a pair of local extrema with the opposite polarity. This establishes a pair of TrueShape vectors that make up one TrueShape descriptor, shown here. Each TrueShape vector within a TrueShape descriptor is inherently stable with respect to lighting and out-of-plane rotation. To achieve invariance to scale and in-plane rotation, TrueShape vectors are normalized. The normalization process is efficient and simple, involving nothing more than taking the ratio of 2 TrueShape vectors that make up a TrueShape descriptor. The resulting TrueShape descriptor is then simultaneously invariant to scale and in-plane rotation while remaining highly stable with respect to lighting and out-of-plane rotation. To be useful, a descriptor must support high classification strength in addition to stability. Classification strength is what allows a computer to differentiate one object from another. This diagram is intended to help describe how echelon segmentation and TrueShape descriptors cooperate to achieve high classification strength. The face image shown here represents the spatial domain, or the first tier in a scale space image. The spatial domain contains the shape information that we see in images. The volume above the spatial domain is the scale domain, indicated in this diagram by a scale axis shown here. This is an actual unified feature region corresponding to the face shown here. Every unified feature region manifests as a separate stationary curve in the scale domain. This is the stationary curve for the feature region used in this example. Shown here is a plan view of the TrueShape descriptor that was derived earlier. This shows a perspective view of the same descriptor, approximately as it exists in the scale domain. This stationary curve links the descriptor to a single feature region in the spatial domain. Each of these additional TrueShape descriptors is also linked to the same feature region by the same stationary curve. The main point is that stationary curves in the scale domain tie multiple TrueShape descriptors to the same feature region in the spatial domain. This allows TrueShape descriptors to be ganged together or cascaded to achieve high classification strength. The arrangement shown here is so useful within the context of computer vision that it is not unreasonable to expect a similar relationship to exist in biological visual processing. This segment of the video presents measured data showing the stability of TrueShape descriptors with respect to out-of-plane head rotation. The data to be presented was measured by manually drawing TrueShape vectors on top of raw scale space data, as I'm showing here. The process was then repeated for the same feature region across multiple frames of the rotating head video shown earlier. Here are a few additional examples of the raw data. And this is a complete data set for one feature region across multiple video frames. The raw dataset just presented is summarized in this graph. The analyzed feature region for this graph corresponds to the area just above the left eyebrow, as indicated here across multiple frames. The data indicates that the underlying TrueShape descriptor remains usefully stable over 45 degrees of head rotation. The stability reflected in this data represents typical performance for TrueShape descriptors. As a point of reference, no other descriptor in the literature comes close to achieving this level of stability versus out-of-plane rotation. For example, descriptors such as SIFT, SURF, HOGS, 2-bit binary patterns, and others only remain stable over a few degrees of out-of-plane rotation. The data shown in this graph corresponds to a TrueShape descriptor exhibiting usable stability over an astounding 92 degrees of out-of-plane head rotation. This measurement, while somewhat atypical, is consistent with the prediction that the upper limit for stability with respect to out-of-plane rotation is 120 degrees. This video concludes with an intuitive interpretation of how TrueShape descriptors encode arbitrarily complex shape information. Shown here are two TrueShape vectors that make up one TrueShape descriptor within a given scale space tier. The magnitude or length of each vector can be regarded as quantifying a relative size proportion among three adjacent feature regions. To clarify, each feature region is represented by a separate local extremum, as shown here. Continuing the discussion, the angle component of a TrueShape descriptor indicated here encodes how adjacent feature regions are oriented with respect to each other. Complex shape information then becomes a compilation of visual proportions across multiple scales. This multi-scale idea is clarified using this diagram presented earlier. Each group of two vectors represents a separate TrueShape descriptor, or equivalently, a separate visual proportion embodying both relative size and relative orientation information. To clarify the next point, I'm moving all the measured visual proportions corresponding to one feature region into the spatial domain. Next, I'm deleting the corresponding stationary curve. Within the confines of a 2D image, all visual proportion information is compressed into one image plane, as shown here for a single feature region. With all visual proportion information compressed into one plane, the total number of permutations among all feature regions in this image is 1.8 million. This represents an infeasible or non-useful scenario within the context of computer vision. The Echelon algorithm expands a frame of video into a multi-tier scale space image. This expansion process down-selects the most relevant visual proportions based on unbiased criteria naturally encoded in each frame. The expansion process also unpacks the down-selected visual proportions, or TrueShape descriptors, as shown here, so they can be individually measured. The down-selected number of visual proportions in this frame of video is an easily manageable 271, 5 of which are shown in this diagram. Thus, the Echelon algorithm reduces the total permutation space by more than 3 orders of magnitude based on fully unbiased criteria. The end result is a theoretically unified framework for enabling fully generalized all-view object recognition with the promise of rivaling the capabilities of biological visual processing. Thank you.